In this video, we will state and prove the Mobius inversion formula. The primary reason to study it is that it actually gives the motivation for why we study Mobius functions in the first place. This will be seen as a vast generalization of the principle of inclusion-exclusion, as well as a generalization of the fact that ordinary generating functions have multiplicative inverses. So here's the Mobius inversion formula. Suppose you have a partially ordered set P that has a unique minimum and maximum element, denoted 0 and 1. Let f be some function on the poset, associating to each element a complex number, and define g of p by this formula. It's the sum over all q less than or equal to p, f of q. Then it turns out you can compute f in terms of the g's. By this formula, f of p is the sum over all q less than or equal to p, the Mobius function of p applied to the interval qp times g of q. So the point is that this is some sort of summation over a function at small values, and it turns out you can compute this function as a summation over g at small values. Granted, I admit it's not clear why you would do such a thing, but this is similar to principle of inclusion-exclusion, where you had sums over subsets. And the point is sometimes you're solving a counting problem where you want to know about this function, some function, and you define g of p this way, and it turns out that you have a nice formula for g of p, then this Mobius inversion formula gives you a nice formula for f of p. So here's the proof. The proof is admittedly simple. You take this right-hand side, you replace g of q with its definition. G of q is by definition the sum over all r less than or equal to q, f of r. And then you just change the order of summation by first bringing the summation out, as so, and then bringing the summation all the way on the outside. By changing the order of sums, you see that here we have r less than or equal to q, and q less than or equal to p. So if I bring the r, you see r must be less than or equal to p by transitivity. And so when I change the order of summations here, I now get a summation over r less than or equal to p. And then the other summation is over q. And we see in order for this summation to work, q must be bigger than p. Hold on carefully. And q must be bigger than r. And then less than or equal to p, because that's the way this order works. We chose r to be smaller than q, and so here we need r to still be smaller than q, times the same Mobius function. But now we see f of r does not depend on this summation, so we can factor it out like so. And so now we have this summation over r less than or equal to p times this summation of Mobius function values. And then how do we finish the proof? Well, the definition of the Mobius function was as the multiplicative inverse of the zeta function. And what do you see here? You're summing over all q and rp, mu of qp. By definition of Mobius function, this is either 1 or 0. It's 1 when r is equal to p, and it's 0 otherwise. And so most of these terms are 0 except the case when r is equal to p, which means for most terms in this summation, this term is 0, and 0 times anything is 0. And so the only term in this summation that survives is the case when r equals p. And what happens when r equals p? Well, f of r is f of p, which is exactly what we want to show. And so this gets a little strange, but it's worth pointing out these Mobius function values are often negative, so this is really an alternating sum. Much like the principle of inclusion and exclusion, you're sort of sieving things in and out and canceling just right to end up getting f of p at the end of the day. And that's what this summation is doing for you. And so to make that explicitly clear, this summation is actually the convolution of the zeta function with the Mobius function. And so because these are inverses, you get this relationship. And so you only get f of p. Similarly, you can actually put all the inequalities the other direction and the result still works. If you define g of p to be the sum over all q greater than p, f of q, then f of p is actually the summation over all q greater than or equal to p, mu of pq, gq. Note, there's similarities in symbols that make it hard to see how this is different than the last formula. The difference is, it's this second coordinate that is varying in the Mobius function, and in the other formula it was the first coordinate, as you can see down here as well. And so that proof is similar, just the inequalities go slightly different. However, I will actually state the strongest version. The actual Mobius inversion formula is this one. If you're given two functions, f and g, from your post set to the complex numbers, then there's actually an if and only if. F of p is the summation over r less than or equal to p, g of p for all elements of your post set. If and only if g of p is given by this Mobius calculation for all p and p. So it's an if and only if statement, whereas the previous statement was only the forward direction. I only assumed this and then showed that this was true. It turns out you can go backwards. If this is true, then so is this. And as we'll see in the next video, there's actually some nice applications of that fact. So before giving the proof, here's the precise statement of the Mobius inversion formula in the greatest level of generality. You have a post set with a minimum element and a maximum element, and you have two functions from your post set to the complex numbers. Then for every element of your post set, f of p is the summation of q less than or equal to p, g of q. If and only if, for every element of your post set, g of that element is the summation of q less than or equal to p, mu of qp times fp. So it's an if and only if. Likewise, there's this dual version, where the only difference is I've replaced the inequalities the other direction. F of p is the summation over all greater values, g of the greater number, if and only if g is computed by summing over the larger values, mu of pq, fq. And usually the way to keep these straight is that we remember a function applied to an interval, this first number has to be the smaller one. And so that tells you where to put the variable. So the good news is one direction of the proof was already done, so I only need to do the other direction. Suppose I define g of p to be the summation over all q less than or equal to p of mu of qp times fq for all elements of my post set. Then let's compute the summation over all q less than or equal to p, g of q. Well, by applying this definition here, g of q is the summation of r over all r less than or equal to q, mu of rq, f of r. But again, similar to what we did before, it turns out you can do a change of summation trick again. If you change the order of summation, then you're summing over all r less than or equal to p, and then over all q in the interval rp. And then when you do that, f of r no longer depends on q, so you can factor it out like so, and you get this summation. And again, this is either 0 when r is not equal to p, and 1 if it is equal to p. So for the terms r, where this is 0, 0 times f of r is 0. And so the only term in the summation that survives is when this is 1, when r is equal to p, and then you just get f of p in that case. And so again, you get this operation. In some sense, there's a way to write this down, assuming you take a linear extension of a post set, whatever that means, that these are actually matrix equations. And you're really just proving that these two functions are vectors that differ by matrix multiplication. Which is one way to do the proof. But it's nice to just do the direct calculation.